was originally mud on the sea bottom, was probably compacted by as much as 3 times. So 15 feet of shale that we see today would equate perhaps to 40 feet of mudstone. Just think of that. How much winnowing would you have to get to produce a typical little thin Cincinnati shell bed? The answer is a heck of a lot. An awful lot. You'd have to take out so much mud that there should be piles of the stuff down ramp in the Seabury Trough. Is there? So that's one other clue. Concretions are a clue. The further we go towards the Seabury Trough, the more we see the development of concretions. Sometimes the shell hash bed itself is very, very thin. And most of what you actually see as a limestone is a concretion. Now let me say just a little about concretions. They don't form at the surface. They form by cements that fill in pore spaces in the mud. And they can only form, we think, during periods of time where that mud package doesn't have more mud dumped on top of it. They form during periods of, well, sediment starvation. In fact, concretions are one of the key arguments for starvation of sediment. And the fact is we see more of them as we go towards the Seabury Trough. In other words, in counter to the pattern predicted by this pure storm winnowing model, we don't see evidence of more sediment being dumped in the basin. We see evidence less sediment was dumped in the basin during these times when the shell beds formed. Shell beds themselves, my colleague Ben Datillo pointed this out. If you look at them, well, you know, we say by the old model they're formed by winnowing, but is that always true? Well, no. Where's the winnowing here? There's plenty of mud in between those shells. That shell bed is pretty packed. It's called a packed stone, but it's still got a lot of mud in between those shells and inside them. And that mud, and here's a critical point, that is limey mud. It's not the exotic type of clay and silt that came in from the mountains. It's homegrown mud coming from algae and stuff. Now, how are you going to make a limestone that has shells and some homegrown carbonate mud in it by winnowing? You can't do that. You've got to take the clay away and somehow, shazam, you replace the clay by carbonate, locally produced mud. Shouldn't happen. In other words, there's an argument against winnowing. And the fact is, it doesn't take too much to see how that could happen during a period of sediment starving. If you hold back all the clays and silts, then the mud that accumulates is just the homegrown stuff, the stuff that's coming from algae and bacteria right in that environment. In fact, starving it is what allows that limey mud to build up. So again, we're seeing, although they can be winnowed, I'm not saying they can't, sometimes they are. Now here's another evidence for starvation. If you look at a number of the tops of the limestone, we looked at the bottom a little bit, not too much, but the tops are very interesting because some of them show hard grounds. Hard grounds are cemented surfaces. They take a long time to form in a hard crust like this. And sometimes they're mineralized. Steve Felton and I have been out to Poe Creek and seen little crusts of phosphate that takes a really long time to develop, plastering right over holdfasts in some cases, and other holdfasts stuck to the crust. These represent really sediment-starved conditions. So we have a further evidence that it isn't just winnowing that's going on. It isn't just the storms. There has to be a genuine slowdown of sedimentation during these limestones. I threw those in. This is, I think Jack took that. But these are from your website. Should have put that on there, but okay. These are just some of the neat things that you can find on the tops of some of them. Okay, so the limestones. Now, we'll get back to a little bit more on them, but now I want to move to the other part of the cycle. We've got the limestone part. We've seen within it evidence for some storm processing, true, but a lot of evidence that suggests very slow accumulation of a lot of shell hash. It's very concentrated shell hash because it wasn't getting diluted by all this incoming mud. What about the mudstone part of the cycle? Go back to my overly complex diagram. It's overly complex because nature's complex. And you see, if you look at the mud in detail, like in a drill core or in a fresh creek bank, and you really start to dissect out that mud, you find something very interesting. it's not just a continuous, gradually accumulated blanket of clay. You find, bang, there's a whole crinoid someplace. Or you find a scour surface, or you find a siltstone layer, which has deep gutters cut into the mud. Or you may find one mud cutting into another one. And this is very interesting. The mud seems to have accumulated in a series of little packages, sometimes up to 10 centimeters shale. Remember I said the mud compacts down to shale maybe 3 times. So 30 centimeters, a foot of mud dumped out at particular intervals sometimes. And we can prove that in some cases. You can find a crinoid maybe going right through that shale package. That crinoid didn't just die and let the mud gradually rain around it. You know what? The muds are really the part that has a lot of events in them. And they're stretched out so you can see the different single events, which I show and list out here. Not that, well, I care deeply when I'm looking at a section, you know, what does that mean? That's probably one bad day in the Ordovician when you get that really oversized storm that brought in the silt. And you see these, a silt scour, a mud layer, and so on. And all of these tell me something very important. Storms didn't go away during the mud time. There were still plenty of storm things going on. But, you know, you can't make a storm-rippled shell bed if you don't have shells. And the muds don't have enough shells in them. What you find instead is a lot of interesting things. Often right off the top of the limestones, you may have noticed this, you'll find some evidence for bryozoan colonies that are in quite good shape. And this may suggest a period of really, again, still relatively slow sedimentation. These rather tough colonies sometimes get broken up, of course, but they suggest perhaps they were getting burial by some of the initial muds, not too fast, perhaps sometimes quick, during an initial deepening when things get a little quieter and perhaps muddier, certainly muddier. Any of you, again, looking at a drill core, and these are again, a wonderful resource. Here's a drill core through coat. You can see it isn't just homogeneous mud. There's a sharp layer there, another sharp layer there, different colors, different grain sizes. The mud is made of a whole series of little packages. Look at them all. You can count them. Some of them are pretty thick, actually, and they represent probably single bad days, you know, compared with thousands of years that may be locked in the limestone. And we see other very clear indicators of storminess in the muds. Drag marks and tool marks, gutter casts. I think the Cope is one of the premier gutter cast sources in the world. And these represent the gradient currents that come sweeping back down the slope and scour the muddy bottom. And I think gutter casts also provide a little bit of a natural experiment too, because if you think about it, the gutter cast is a little channel cut in the mud. And it accumulates a channel lag in its bottom of any of the heavier particles that didn't get winnowed away, or bigger particles. Now if you look at that, we looked at over 100 gutters